start recording. Okay. Uh, so I'm sorry that you have to come to class today, but based on the calendar, today is the first day. Supposedly there is no class. However, during the semester, I have to travel several times. So if I also skip this one, we don't have enough lectures. Okay, and let me introduce myself. Oh, you may want to see wider screen. Hold on. How do I? Try this. Yes. Okay. Am I still recording? Let me double check. Yes. Okay. So, my name is Po-Ting Ling. I'm the professor from Department of Mechanical Engineering. So originally, this is a course in Department of Mechanical Engineering, and it's a qualified course for PhD. So who is PhD from mechanical? Okay. So you guys need to do a good job, and I remember you need to get 80 or more to pass the qualify. Okay, so don't skip a course, don't skip a lecture. And I know some of you are master students, some of you are from the Intelligent Manufacturing Research Institute. So totally okay. You can participate the course, no problem. I am leaving my personal information here, so in the future, if you have questions, you can send message to me. So my school's email is this one. And if you want, this is my personal email and also my Facebook account. If you would like to monitor what I'm doing, you can add me as a friend, but I will also monitor you. So if you skip a class, not handing homework, doing a bad job, and I see you what you're doing on Facebook, I will say something bad to you. Okay, don't judge me. About my line, if you want to send me personal message, this is my line, that's fine. And my cell phone is here. Okay, so you can find either way to contact me if you want. And in this course, we have a Facebook group. I think the TA already sent you the information, so you can use it to come to this Facebook group. I rarely use Moodle. So if you send me message on Moodle, I cannot see it. But I will send all the course messages to Moodle and Facebook group. Mostly I will be on Facebook. So if you want to really talk to me, Facebook is a way, okay? And I would like to use this way to give lecture notes. And if you miss anything, we have videotapes. As you can see, we have a camera right there. And I also record the monitor. But sometimes the video recording fails. So it's possible in the future, for example, during the video recording, some part doesn't have video or freeze, only audio. So the best way to learn is in the lecture. Okay, we can communicate face to face. And I would say the videos are for you to review and as a backup. Okay. Everything, all those videos, and also my notes on iPad will be posted on YouTube, and also I have a website. I will post on website, so you can easily access. Let me show you maybe from here. Okay, let me. Okay, so if you go to my lab's web page, there's a online lecturing, and I post all the course materials on this web page. At the bottom, there's optimization. So I have been collecting videos and example codes, handouts, my notes on this page, but I'm still collecting. Some information were not posted, and this semester I will be sending the information on this webpage. Okay, so you will find them easily later on. Okay, and in my handwriting, you realize sometimes I don't like to write in a very clear manner. Sometimes when I write really fast, you may not realize what does one character mean. So right now I'm going to write down how I usually write English on the board. So in the future, if you see some symbol you just don't know what it means, you can go back here. So this is how I write A, B, C, D. No, this is not my cue. No, I forget what is my cue. Maybe like this, or sometimes this. Yeah, as you can see, I like to mix different styles into. This is me. I'm sorry. Okay. The capitalized A, B, C, D are fine, but the small ones are harder. So the hardest one probably is this. Sometimes it's like this. Sometimes I do this. S. Those are the hardest. Okay. When I was a graduate student, I went to USA for graduate study. There's one course, one professor gave messier notes. I couldn't understand what he was writing, and USA professors sometimes write down something, but they talk about something else. So I couldn't match the writing and what he said. I couldn't match them together. So there's one word I really don't know what it means. And as a graduate student in USA, I cannot fail. I cannot fail any course. I need to get A for all the courses to keep my scholarship to keep in USA. And I worried if I cannot understand a word on his notes, that could cause a problem. Maybe that's something important. So at the time, USA professor, they write really fast, they talk really fast, they don't wait, and when they are done, they just clear the board. It's they use the traditional blackboard. They don't use iPad. So I have to write it down really fast and then try to focus on what the professors were talking about. So at the time, I decided to do one thing. I consider that handwriting as a drawing. I copy the drawing exactly like how he wrote on the board. Even though I don't know what it means. It's really a very messy sequence of handwriting. I write it down in my notes. And 2 years later, in USA, if we want to study for PhD, we need to pass the qualifying exam. It's a real exam, not like Taiwan Tech. In Taiwan Tech, if you pass this one, you are qualified. You can say you are PhD candidate. But in USA, you don't need to pass the course. You don't need to take the course, but you need to pass the exam. It's an additional exam. So every semester, there's a date. The professors who take care of the course will give the exam. Usually, the exam is in a similar style to the final exam of his course. So we are recommended to take the course, to go through the entire course, pass the final exam. So what you need to do next is to go to the qualifying exam and then do the final exam again. Okay, so this is what happened. And I took that course 2 years before the qualifying exam. So 2 years later, I need to prepare for the qualifying exam, and it's a lot of coursework. Let me show you my course notes. This is one course. This is all my handwriting. This is only one course. So this is the first time I took optimization. And because my advisor was teaching optimization, so I took the course second time. This is my second time of writing, and my second time of notes. Okay, so I took the course actually 3 times. So what happened was, back to the story. Poor handwriting from the professor. I copy it on my book. I never understand what it means. 2 years later, when I prepare for the qualifying exam, I realize I can recognize the poor handwriting. Because I'm so used to American writing in the following 2 years. Whatever they write, I can understand. So if you guys cannot understand what I'm talking about, or something I wrote, or anything that you learn in your graduate study, you just need to practice more. You just need to give yourself some time. Okay? Including how a professor speaks English. When I was in USA, my math teacher was from Korea, and some professor is from Turkey, and some professor from not USA. Some professors in around the world came to USA to teach. So everyone is speaking in a very different accent. And of course, if there's something I couldn't understand, we always raise our hands and say, "Hey, professor, can you repeat that again? Or can you explain again?" So in Taiwan, students tend not to raise their hands. I encourage you to ask me questions if you couldn't understand anything. Okay? So that's the introduction of myself. And we are going to talk about the scheduling of this course. So for we are having Mondays, right? Monday course. And this one is unique. This one is Saturday. But the next one is gonna be Monday. Oh, by the way, sometimes I'm switching the monitor, iPad. Sometimes the projection doesn't show what I want to show you. Just tell me, hey, professor, you are not showing the right screen. Just speak out. Raise your hand. Don't be shy, okay? So supposedly June 5th is the last week of our course. So let me tell you what I'm planning. Today is introduction, and next week we're going to learn something about Newton's method. Okay, and on the 27th, it's a holiday. On the 6th, also Newton. But on the 6th, I can come back on 6th. 20, okay. So I can give lectures on both. On March 6th, I will be coming back from Australia, and I came back to the airport. I arrived at the airport at 4 a.m. in the morning. So probably I will get my car at 5 a.m. I will come here. Or I come back to take a shower and then come back. So if I come here and have oily hairs, smelly bodies, please don't judge me. Yeah, I took a 15 hours flight. Okay, so on the 13th, I'm traveling. I'm traveling to USA. So I cannot give lecture on this one, but I still want you to learn. So on this one, I will teach something called the steepest descent, and I will give you a teaching video. So you may need to watch a video for this one. You don't need to come to the lecture, but just watch the video at home. And the next time, it's a method called conjugate gradient. And also, I'm still in USA on 20th. I come back on 21st. So for these two, I may need to give you course videos. 27th, we are learning something called linear programming. On the 3rd, it's a holiday. As you can see, we have so many holidays and so many travel. So I don't. Then we have midterm week. Midterm. And then in this course, everyone needs to, maybe not everyone, because we have too many. I want you guys to get into groups, and each group need to present something. And on 17th, you are going to give proposals of of your final project. And I will tell you more about the project later on. 24th, something called KKT condition. May 1st, something called quadratic programming. And then genetic algorithm. Multi-objective. Disciplinary, uncertainty, and then neural network, then final week. So this is gonna be our final presentation. Okay, so one thing we need to discuss: do you prefer more exams or fewer exams? More exams means we can have fewer materials for each exam, but we need to do exams multiple times. So for each exam, for each small exams, we have lower grades. If we only do one exam, that exam is so important. If you fail that one, you can almost drop the course. Right? So, who likes more exams? Smaller exams? Who likes more? Don't be shy. Everyone needs to raise his hand. It's okay. Right now, the scheduling is like a one exam. Who likes more? So I can cover little smaller area for smaller range for exams. So who likes more exams? Okay. Oh, okay. No, keep your hand. I need to count. Okay. I think smaller exams win. Okay, if that's the case, we need to reschedule a little bit. Do you like take-home exam? Okay, so maybe we do oh no, I think we can. Okay. So maybe I can do this, and we can have our exam 1 here. And exam 1 is gonna be covering all kinds of Newton's method. I still use Newton's method nowadays, so I really like Newton's method. So it's gonna be our exam 1. And for the exam 2, I guess we don't have midterm. It's not midterm anymore. Maybe we can. Oh, let me check my schedule on June. Hold on. I have to travel again on June 12th. June 12th. Oh, okay. So it's impossible to get one extra week. Okay, I guess take-home exam. How about this? We will do take-home exam right here. So this is gonna be number 2, and basically steepest descent and conjugate gradient. Okay. So I think linear programming we can already do another take-home exam, or maybe yeah. So just linear programming. That there will be. It's like doing a homework, right? But it's like an exam. It's like a homework and also like an exam. Okay. Score-wise, I call it exam, but for you guys, it's like doing a homework. Okay. So and usually for take-home exams, I will give you some time, maybe a week or 2 weeks to finish it. So you can just treat them like doing homeworks. How about we do take home? Who doesn't know how to use MATLAB? Raise your hand. It's okay. Okay, only 3. You can learn. Learn to use MATLAB. It's very easy. Take home MATLAB exam. Okay, so it's gonna be F min Kang. Okay. I think we just do 4 exams. So for the following, GA and multi-objective, uncertainty, neural network, they are more advanced. So it's really difficult for you to it's really difficult to be covered inside exams. Okay, so we can do 4 exams, and 1 project, and also attendance. Attendance 10%, project. So exams 10 for each. So this is 40. So project 50. Is that okay? Do you want more for exams? Okay. That should be good. Okay, now today I'm going to give you some fundamental knowledge and information about optimization. Okay. So there are 3 very important, you can say, components, or 3 very important factors you need to be worrying about in optimization. So we can say, or 3 important things. So one thing is your objective function. could be multiple ones. And the other is your variable. Could be multiple ones. Okay, the third is called the constraint. Also could be multiple ones. So there are the three important things. If I give you an exam and ask you what are the three important things in optimization, write these down, you get points. Okay? So let's try to formulate a description for optimization. Okay? I forget the names. Oh, let me create a random generator so whoever being picked by Google answer the question. Okay. So one more time. Hika? Okay. If you are looking for a perfect girlfriend, what are you looking for? Her height, her optimizing your girlfriend. Give me something that you are looking for. How pretty? Pretty, right? Okay. So if there's a meter calculating how beautiful a girl is, let's say from 0 to 10, then you are trying to maximize the beauty level of your girlfriend. That's optimization. Maximizing some number. So that's one optimization. Okay. So each person may have a different beauty level. So if you are choosing different ones, but you can only choose one, then that's your variable. Let's say there are 10 girlfriend candidates in front of you. So if I give numbers to them, 1 to 10, then my variable is the selection that you make. So what you can do is so easy. Just use that beauty meter to evaluate each person, and the highest score, the person with the number has the highest beauty level, is your optimization goal. Okay, but can you give me a secondary? Give me a condition that you, in your mind, that candidate must satisfy. For example, cannot be older than 30 years old. Age. Age, yes, age gap. Okay, good. So let's say, how old are you? 20, 25? 28? Okay, so for example, maybe looking for the journey of looking for your girlfriend takes a long while. Maybe. So there is a limitation. For example, the girlfriend candidate for you cannot be 3 years older than you, but could be very younger than you. You are greedy. You just cannot accept older ones, but younger ones you like. For example, so there is a constraint. The candidate's age must be smaller than or equals to your age plus 3. So that's so-called the constraint function. So each candidate could be having a different age. So whoever is not satisfying the age condition is not the one you want. Even though she looks so beautiful, like a supermodel from Korea, it's out of your age criteria. She's out. Unless you change yourself. I'm greedier. If she's beauty enough, I don't care about age. Then it's a different formulation. Okay? So, optimization formulation really depends on how a designer makes decisions. And although in real life you cannot do optimization like that, you cannot use optimization to find girlfriends. You will never find one. but that's just one, just a cute example. Okay, so, but in that cute example, you realize when I try to describe an optimization problem, I try to quantify them. Like how beautiful a person is, we need to quantify the level of beauty. Otherwise, it's very difficult to solve. If a problem is not written in numbers or functions, it's really difficult to solve. Okay. So, follow up to that example. What is difficult to solve? If there's a description, for example, I need a girlfriend who. What is difficult to quantify? What is difficult to quantify? Now I cannot think of anything. I'm too engineers. It feels like everything could be quantified. Okay. I cannot think of anything. Sorry, my engineering brain feels like everything can be quantified. So let's skip that example. Let's get back to how we can write it down. Okay, so since most of us are mechanical engineers, so let's get back to a more mechanical engineering example. Let's say you are manufacturing a mechanical part, and for example, it's a metal plate. Okay, and you can change the thickness and also the material property. So for example, Young's modulus. And what's the usual objective? For example, you usually would like to have lighter weight, so you want the weight to be lower, right? Can someone tell me what is the lightest design for this plate? If my variable is the thickness and also the Young's modulus. Zero thickness has zero weight. So if you put this formulation, if you put this description in a plate design, you want the minimal weight. Zero thickness is the solution, but it doesn't make sense, right? So you would like to have constraints. So when in your design, the result makes sense. So for example, for the constraint, you have some strength condition. So maybe the strength must be strong enough. So for example, larger than certain level, certain value, some value, okay, something like that. So the decision of thickness and definitely will affect the weight, and of course it will affect the strength, right? And Young's modulus definitely changes the strength. Does it change the weight? It's like you are picking different materials. If you use copper or iron or different kinds of materials, when you make the decision, the density changes. And since the density changes, the weight changes as well. Okay, so actually it affects the weight. So we can call this a function of f. We can call this x1, we can call this x2, and we can call this g. Okay. But in optimization, sometimes we don't like strength to be g. Okay. Let's call this s. Okay. And in optimization, in many times we would like to rewrite this equation into a different format. For the sum value, let's call this s lower bar. I will tell you what is a lower bar. But in optimization, we usually likes to rewrite this into the following. Oh, sorry. Something was wrong. We like smaller than or equals to. We don't like larger than. And we like the right hand side of the sign to be of the equation to be 0. And we like to call the whole thing right here in the front as g. So g is a function. So if you reformulate the whole thing, you realize you have a function of f, and it's a function of x1 and x2, and you have a function of g. It's a function of x1 and x2 as well, and it equals to some value s lower bar minus some s function, which is also a function of x1 and x2, and this must be smaller than 0. You have these two functions, and we need an action of optimization. This is the action. The goal is to minimize f. So we usually write minimize in front of the objective function. How about the constraint? We like to use something called subject to. And for short, many people directly write this. So ST represent subject to, not such that. So when you try to describe this, for example, when you write a paper, you want to describe this, you can say a problem is defined to find the optimal solutions of, you can do this, x1 star x2 star to minimize the objective function f of x. This time I use a vector subject to the constraint function g of x smaller than 0 or equals to 0. Okay? You need to know the language of optimization. It's really helpful for you to understand what's going on. Because in some papers, they don't write down this. They just write down the description like this. Why do they do that? They want to hide their secret. They don't want to tell you exactly how they do optimization. Or, for the entire research, optimization is a smaller, very small step. Just one sentence, and it's done. Just one sentence. In the entire paper, there's only one sentence telling you that's how I did optimization in this particular step. But it doesn't tell you what exactly was done behind it. The paper even didn't tell you what method they use. But there's one description. Okay, this optimization was formulated like this, and we did something to find the optimal solutions. Okay, so let me tell you what is star and what is the lower bar and upper bar. So people sometimes would use this lower bar and upper bar to represent, we call lower bound, and we call this upper bound. I sometimes see people do this. Oh, sorry. Maybe capital L is better. I sometimes see people do this. Also, sometimes people do this. The upper superscript. It's fine. No matter what kind of symbol they use, they are all common. They can be seen in papers. But if you are the author for the paper, you need to define them. Okay? So what's the star? So if I have a design variable, it's a vector. The component includes two components in there, two numbers. I use a vector to put them together. So variable means it's a decision that can be changed during the process of optimization. So they are numbers that you change when you are searching for the optimal solution. When you find the optimal solution, you can put a star in the superscript position just to indicate this is the optimal solution. And of course, you can do this as well. Okay, and how about when you plug in the optimal solution to your objective function? Your objective function basically is the optimal value, right? If you plug in optimal solution to your objective function, sometimes I have seen people do this. Just say F star. But whenever they use those symbols, You need to describe them properly. Okay? Now, there are some more terminologies that we need to learn. If you have a solution, for example, gx larger than 0, we mentioned we are looking for g that is smaller than or equals to 0. So if you have a point, let's say there's a point x, I don't want xa, some point in the design space. But when you plug in that point to your g function, it doesn't satisfy your constraint. So this is not satisfying the constraint. We call this point infeasible. Not useful. You cannot say not useful. You can infeasible. The word infeasible means exactly not satisfying the constraint. So otherwise, in other case, if the point is satisfying your constraint, you will say this point is feasible. Okay? So sometimes when we are dealing with optimization, we care about something called feasibility. When we say hey, we need to care about feasibility, we need to check the feasibility. That means you care about whether the design point is satisfying the constraint. It's like how much the design point is satisfying the constraint. So we use the word feasibility. It's like the condition of these. We use the term feasibility. And for optimization, there's a term called optimality. So optimality cares about whether a design point is optimal or not. So design point or design variable is optimal or not. So if you can find a design point that is meeting the criteria of optimality and feasibility at the same time, it's the optimal point. Okay? So optimization is like this. It's a design problem. There are 3 factors inside. You have your objective function. You either want to maximize it or minimize it. And you have your second factor, which is the variables. When you change the values of the variables, the objective function changes. The value of the objective function changes. Meanwhile, you have several constraints. Also, usually there are also functions of your design variables. If you change the values of the variables, the condition of the constraint changes because the point could be feasible or not. If you keep on searching by changing the values of the variables until one day you realize there's a point that truly minimizes the objective function, I cannot minimize more. And also that point satisfy the constraint. That must be the optimal solution. Okay. Yes, go ahead.
The value of G, which is x factor A is larger than 0, or sorry.
Here, G.
No.
Here.
Yes.
Ah, you mean
G
why we don't have this?
invisible and visible, and the value 0, and
Value 0 is feasible.
I mean, no. Is it always, because the value of G is always a value, right? So is it okay if the value is above 0, slightly above 0, or should we change the parameter,
The constraint.
yes, the constraint, or somehow, or so
Yeah.
we have many optimal design if we can change this
Yeah.
variable.
Very good question. When we are solving an optimization problem, we treat everything ideal. It's like I know in the world there are uncertainty. When I ask a machine to build this cylinder, I'm asking for diameter the diameter of maybe 8 centimeters, but at the end it's 8.1. So there is always a tiny difference between the math and the reality. We call them uncertainty. And like you said, when I design for optimization, if I'm asking for, if the constraint value for this is about the weight, and let's say this is 100 grain, and at the end it's 101, it's 1 gram over my constraint. Do I still am I still satisfied? So in real life, those tiny tolerance exist. So usually there are several ways to do it. One is in your formulation, you already apply that tolerance into your function. So what you get at the end still have that gap. Or you keep the function like that, but when you solve for optimization during the process, you don't need to reach to the optimal. It's like there's a gap, but I'm so close, I'm done. I don't evaluate more to find even better solution. Or there's something that is my expertise. It's called the design optimization with uncertainty. So it's there's statistical analysis involved inside optimization. So that would be introduced on May 22nd, uncertainty. So I need you to learn the fundamental, the ideal the ideal world of optimization. Later on, when we deal with real world design for the advanced topics, I can tell you more. Okay, very good question. Okay. Yeah.
Is there any reason to use the half error to identify the vector?
You mean which one? Say again.
The
dx.
x, x1, x2.
Oh yeah.
Means the half error. So is there any reason to identify?
R.
Normally use the full error to identify.
You mean the capital L?
No, the x.
X.
Yeah, use the half error.
Half arrow. Oh, you mean for the vector?
Yeah. But we normally use the full error. So is there any
Half arrow. Okay.
Yes.
I like half arrow.
Oh, sorry.
If you like the full arrow, it's your choice.
No, I just
In-
is there any reason to?
In my educational background, everyone use half one. But if you are using the full one, maybe in your country, you guys use the full one. I use the half one. My colleagues all use the half one. I don't know why. And in many books, they use the half one. Right? But it's a vector. Okay. Let me see what I can talk about today. Maybe I give you one example, a real math problem. Okay, who knows the answer? Who knows? If someone knows the answer, you can go. You can go back home. Okay. How? I haven't teach you anything to solve it, but when I was a graduate student, I always try to make drawings to help myself. So now I'm making some drawings to help you understand what's going on. So it's a 2D problem, right? So here's your first variable, your second variable. First, what you need to do is to make a drawing of the objective function. And let me show you what the objective function look like. It's a if you go to Google, you just type in x1 squared plus 10 times x2 x2 squared. If you do that, do you know what Google will do? Does anyone know what Google will do if we type in this? It didn't, no. Maybe use x and y. So x squared, do it again. X squared plus 10 times y squared. Maybe this. What happened, Google? Google didn't do it. In the past, Google will do something, but what happened? They switch that function somewhere. Maybe formula? No, not formula. No, they made a change. Maybe graph. So sad. Google in the past, you just type in, it will make the drawing for you. Now I need to figure out how Google can do it. Oh, you need to type in y equals to nowadays. Okay. How about this? No, it doesn't do the magic. In the past, it will make a 3D contour. No. By Google? So somehow my Google doesn't do it. Am I using Google? This is Google. What? You use Safari? Okay. Safari and Google. Okay. Let's try it. No. My Google doesn't do it. Let me try my laptop. Okay, laptop. Somehow my iPad doesn't do it. But if you use a laptop, for in my case, this time it doesn't. No, it doesn't do the contour. Come on. In the past, it really can. Oh, here. Okay. So if you make a drawing of, let's stop this. Stop. So this is basically the red one is X. So I should do it like this. The green one is Y. So here is X, here is Y. This is how the function look like. And for optimization, what I would like to do is make a contour of it. So the contour will look like this. It's not in the right scale, just approximately you can make a drawing like this. Okay, it's a so-called a contour. Okay. If you want to make the contour so accurate, then you need to figure out the coordinates of points, make right drawings. So, for example, this ellipse is the like a first level of the contour. It could be the level of f equals to 10. So here would be the coordinate of 0 and 1. Here could be the coordinate of 10, 0. So that ellipse covers all the points that has the objective function value of 10, right? And let's say this is another level, f equals to supposedly 20, is it? No, not 20. 40. Because over here, over here, this is 0, 2. So if you plug in to f, it's gonna be 40. So for here, this would be what? No, I made a mistake. Sorry. This should be square root 10. Right? Yeah. And this should be square root 40. If that's a level of 40. Yeah. Correct? Right? So from here you can tell, without the constraint, where is the optimal solution? It's right here at the middle. 0, 0 has the lowest function value. You cannot find any other point that has lower function value. Okay? How about x1 plus the constraint function? What do you do for this constraint function? What you can do is make a straight line like this. And do this. What does that mean? That means at the lower left corner or lower left area separated by this line, will have function value x1 plus x2 smaller than 3, right? On this line, it's going to be x1 plus x2 equals to 3. On the upper right area, it's going to be x1 plus x2 larger than 3. And because I'm looking for greater than 3 or equals to 3, so my feasible region includes this line, this entire, maybe just this upper right area represent the feasible space. Feasible space, or you can say feasible region. And for the lower half, it's your infeasible space. So where is the optimal? It's somewhere on this line. And it's at some position that has the lowest function value. So the optimal is right here, somewhere right here. There's gonna be a contour where you have a tangent point, tangent to the green line, and that point is your optimal, because that's the only point that you can find that has the smallest objective function value and still inside the feasible space. Can someone tell me what's the coordinate of it? Maybe not easy. Maybe you need to do some math to figure out. Do some calculus or algebra to, if it's a graphical approach, you need to do some algebra. But in this course, I'm going to teach you how to do it very effectively. This course is going to cover so many methods. The methods figure out how to solve it. Okay? Let me show you some of my previous papers. Maybe this one. This is a paper I wrote 15 years ago, 2009. Yeah. So in this paper, you can tell, because there are so many symbols to be used, at the beginning I need to list all the symbols to explain, okay, what does each symbol mean in the paper. Now you understand what does it mean, right? So this is exactly what you're looking for. Optimization with uncertainty. There are probability inside the constraint. A probabilistic design optimization is then formulated as follows. minimizing a function called y. It's a function of d. Sometimes we write down the variables underneath the minimization, the mean. The reason why is because sometimes this function has some other parameters, but it's not your variable. So sometimes if you write down the variables here, people understand, okay, this is the variable. This is what you are varying. And if you have some other variables that is not involved in your optimization, you don't need to write down the other parameters. So let me show you one example. If I do this, if I'm minimizing f of x1, x2, but I only say x1 here, that means I'm not going to change x2. Okay, so this is the representing which one is the variable. So in this case, this is just like a parameter. It's not something you want to change.
It's like constant.
No, it's like just a symbol representing some number. But during the optimization process, you will change what you indicate here. For example, there's an initial value 1, and you may want to test, is it 2 better, is 3 better, is it 4 better? But this process doesn't ask you to make a change of x2. So supposedly you should not change x2. Okay. So what's happening is when people write a paper, they don't tell you exactly what they do. They just write it down in this way, and whoever understands optimization already know what's going on. So you guys need to take this course and figure out how we describe optimization. Otherwise, in the future, whenever you read optimization papers, you will be struggled. Okay, because we assume people understand this. Okay, and from here you can tell. Whenever I have a mathematical description, I will use where blah 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 to explain every symbol I use. So I encourage you, when you write a technical paper, when you have this kind of mathematical description, describe clearly. Describe every symbol you wrote. Okay? And you can go read so many other papers. They describe this kind of stuff in many different styles. This is one style. This is the most boring style, but it works. Technical writing is boring. Boring is fine. Okay? So, let me see. Like, in my problem, there's another optimization. I have multiple optimization process. Yeah. There's another one right here. So, in a paper, when people write this, you may want to know, okay, so how to solve it? The paper doesn't tell you. Because the way to solve it is inside a lecture the author took in the past. We assume you should know how to solve it. So that's why you guys are here. Okay. Let me see. Here's another one. This is like a optimization process. I will show you some process like this in the future. But right now, you probably couldn't understand what's going on. Okay. Did I mention the contours? the color, the rainbow color contour, basically is the objective function. And the solid straight lines are the constraint. So by what I showed you earlier, you can already kind of tell what's going on. It's a contour, the objective function is a linear function, and if the optimal is here, definitely this area is representing lower value. So it's like you have a linear objective function, and you are trying to move from here to here. And you have two walls, two constraints, and this corner basically holds the design point. So it's like there's a searching procedure, and then when it stops right here. So I sometimes describe the optimization process as skiing, snow skiing. It's like the objective function is a snow mountain. You're at the top, and you want to ski down the mountain, go to the food court to have a dinner. You're all the way down, and when you are skiing, sometimes you couldn't tell where is where. So the skiing process is like your optimization process. You don't want to ski into the feasible space. It's like you are falling from the cliff and you died. It's like you can only ski in a safe area. You don't want to get out of the safe area. Okay, so for me, I feel like optimization process is like skiing. Okay. Yeah, go ahead.
I asked about the constraint. Is it always the constraint? I mean, in this problem. Is it always as
No, it's not always having a cross. We design the problem in this way so people can easily visualize what's going on. But in real life, the objective functions are nonlinear, so they are not straight lines. The constraints are nonlinear, they are not straight lines. Okay, I can show you some other, like this. The objective function is a contour, nonlinear contour. And like this one, the constraints are nonlinear. In real life, nothing is linear, right? Finding a girlfriend is not linear. It's not like if I have one step closer to her, the way she likes me upgrade 1 point. It's not like that, right? The real life is not linear. Okay. Okay, good. So this is one paper I wrote in the past, just to support about what I talk about today. Let me see if I have any other terms would like to show you. Maybe not. What time is it right now? Okay. Because today is only the first day. I don't want to occupy too much time. But in the future, later on, from today's lecture, you can tell how much I like this course. I really enjoy optimization. I even took the course 3 times, right? And I don't even need to check my notes in order to give the lecture. I know so much about optimization. I love the course. So I would like to share what I have learned to you guys. And I could be talking nonstop. So in the following courses, for the entire 3 hour, if you really need to take a break, you can let me know. Hey, Professor, can we take a break? Otherwise, I will be talking. I won't stop. Okay, because I love the course. I love this this course. Yes. Okay, so I guess this is what I want to cover today. Before you go, if you want to come by and check my course notes, you are free to do so. Just to have a feeling about my learning process in USA. That's it. That's it for today. Thank you guys. I will put my notes here just for you to just have a feeling. And you can go. And if you have any other questions, come here.
Yes. When will this video recording